Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel. Today, I'm going to present epoxy hybrids. Various polymers, bores, thermostats, and thermoplastics can be blended and co-reacted with epoxy resins to provide for a specific set of desired properties. At high levels of addition, these additives result in hybrid or alloyed systems with epoxy resins rather than just modifiers. They differ from reactive diluents in that they are higher molecular weight materials that are used at higher concentrations and generally have less deleterious effects on the cured properties of the epoxy resin. The most common are nitrile, phenolic, nylon, polysulfide, and polyurethane resins. These hybrid epoxy adhesives are generally used for demanding structural application, such as in aerospace industry, where the optimal properties from each component are desired. For example, epoxy is generally used to provide good adhesion and processing characteristics. They are blended with these resins to provide additional improvement in the properties noted. For example, with phenols for high temperature resistance, with nylon to embed toughness and peel strength, with polysulfide to enhance elongation, with vinyl to reach high resiliency and peel strength, with nitrile to toughness and peel strength and also chemical resistance, with polyurethane to enhance peel and impact resistance. Hybrid resins have been used to improve the flexibility, thermal shock resistance, elongation, heat distortion temperature enhancement, and impact strength of unmodified epoxy adhesives. However, there are also be some sacrifice in certain physical properties due to the characteristics of the additive. These alloys result in a balance of properties, and they almost never result in the combination of only the beneficial properties from each component without carrying along some of their downsides. Strategies for hybrid resins or how they are applied. These blends can take a number of different forms. The added resins may be reacted with epoxy resins, or it may be included in the unreacted modifier. The modifier may be blended into a continuous phase with the epoxy resins, epoxy alloys, or precipitated out as a discrete phase with the epoxy resins matrix, as is generally done in the case of toughening modifiers. Epoxy hybrid adhesives are often used as film, supported and unsupported, or tape because of ease with which formulated systems can be dissolved into the solvent and applied to a carrier or deposited as a freestanding film. Some systems, notably epoxy-urethanes and epoxy polysulfides, can be employed as a liquid or paste formulation because of the low viscosity characteristics of the component. Epoxy nitriles are single-phase alloys of acrylonitrile butadiene, nitrile resins, and epoxy resins. Since the nitrile rubber usually contains no groups that normally react with the epoxy groups. Carboxyl-terminated butadiene acrylonitrile liquid rubber, or CTBN, has been widely used to toughen epoxy resins. The level of acrylonitrile can be varied from 0 to 28%. If a large elastomer concentration is used, no phase separation will occur to form precipitates. The single-phase epoxy nitrile adhesive is made by choosing an epoxy resin curing agent combination in which the nitrile rubber is soluble. Therefore, after cure, the adhesive is clear, rubbery, single-phase resin. The nitrile component is introduced into the epoxy resin at elevated temperatures. The blend is cured with standard epoxy curing agents and catalysts at elevated temperatures. Nitrogen-containing curing agents are generally used with these modifiers because they catalyze the reaction of the carboxyl group with the epoxy functionality. Relatively high molecular weight for rubbers bigger than 20,000 is used. The final product is generally an adhesive solution or an adhesive film. The film is widely used in aircraft structures where a high degree of peel strength and good resistance to moisture is required. For adhesive application, the main focus is usually on improving shear and peel strength. If this blend is incorporated in epoxy systems, a significant improvement in toughness and elasticity in the cured bond line resulted, which means a high tensile shear and peel strength. As a result, nitrile modified epoxy adhesive have found applications in bonding airframe structures and other applications where a combination of high tensile strain with peel and impact resistance is required. Nitrile elastomer offer a unique blend of properties. These widely used synthetic rubbers features flexibility and resistance to wear, mineral silicone, synthetic oils, hydraulic fluids, and fuels. They are resilient and have low creep and superior abrasion resistance. Nitrile rubbers are commonly used in the automotive, marine, healthcare appliance, aerospace, and other industries. Specific applications include fuel lines, automotive transmission belts, rollers, water pump seals, hydraulic hoses, cable jacketing, and grommets. The good low temperature properties of the flexibilized epoxy resin systems are due to the increased mobility of the segments. Therefore, these systems show notable strength, impact resistance, and temperature shock resistance. Moreover, using CTBN, the crack density, surface area cracking per unit volume of sample of the cured resin is reduced significantly. These systems were found useful for prepreg for various types of laminates. Prepregs having minimum bonding capability, centrifugal casting, filament windings, and certain types of brand layouts. One of the largest area of use of a nitrile rubber modified epoxy system is in the printed circuit boards area. The epoxy nitrile adhesives were introduced commercially in the late 1960s. They consisted primarily of diglycidyl air bisphenol A epoxy resins modified with carboxyl terminated butadiene nitrile or CTBN rubber. These first nitrile copolymers were available from B.F. Goodrich under the trade name of Hi-Car. These epoxy resin systems were at one time predominantly, indeed almost exclusively, the domain of structural adhesive industry. Adaptation of some of these systems and the associative epoxy technology surrounding carboxyl terminated liquid rubber have produced a growing high-car epoxy alloy consumption in epoxy applications other than structural adhesives. Compared to nylon blends, one advantage of these nitrile epoxy formulation is that they provide a higher degree of peel strain retention at sub-zero temperatures, which is achieved by bulk elongation. The nitrile epoxy adhesives also provide better resistance to moisture. Employing nitrile in the epoxy systems often result in a degradation in heat and chemical resistance. Typical composition of these formulations have been presented here. In commercial samples, often diglycidyl air bisphenol A systems are used and DDS is used for curing. Epoxy phenolic adhesives are made by blending epoxy resins with phenolic resins to improve the high temperature capabilities of the standard epoxy resins. These adhesives are generally based on blends of solid epoxy resins with Resol-type phenolic resins. The epoxy resins component is often not the predominant component in the blend, depending on the end properties required. They are commonly used for bonding glass, ceramics, and phenolic composites. Because of their relatively good flow properties, epoxy phenolics are also used for bonding honeycomb sandwich composites. Phenolics are compatible with epoxy resins and will react through the phenolic hydroxyl group. The amount of phenolic resin used is generally much greater than that of required for crosslink with epoxy. The epoxy impart toughness and the phenolic increases the heat resistance. In these systems, the excellent thermal stability of the phenolic resin is coupled with the valuable adhesion properties of epoxies. Adhesives based on epoxy phenolic blends are good for continuous high temperature services in 175 centigrade range or intermediate service as high as 260 centigrade for short terms. They can be used even at 370 centigrades. They retain their properties over extended temperature range. Epoxy phenolic adhesives are exceptional in that they have good adhesive properties at both elevated and low temperatures. Although the tensile shear strain of epoxy phenolic adhesives remains steady over a very broad temperature range, it is not as great as that of epoxy nylon or polyurethane adhesives at cryogenic temperatures. These adhesives are available as paste, solvent solutions, and film support on glass fabrics. The adhesive film generally give better strains than do liquid systems. Cure require a temperature of 175 centigrade for 1 hour under 15 to 50 psi pressure. Epoxy phenolics developed in the early 1950s and they were the first high-temperature epoxy adhesives to become commercially available. The first epoxy phenolic adhesives were developed at the Forest Product Lab (FPL) as a result of research aimed at high-temperature military aircraft adhesives. Epoxy phenolic adhesives were developed primarily for bonding metal joints in high-temperature applications. Their first major application was to join major aircraft components. First, commercial epoxy phenolic adhesive formulations generally contain more phenolic resins than epoxy resins, and as a result, they have good high temperature and chemical resistance properties. But the adhesive suffers from relatively poor peel and impact strengths. Their resistance to weathering, oil solvent, and moisture is very good. However, because of the rigid nature of the constituent materials, epoxy phenolic adhesives have relatively low peel and impact strain and limited thermal shock resistance. Most adhesives of this type have limited storage life at room temperature and are generally stored under refrigerated conditions. Typical composition of an epoxy phenolic adhesives has been presented here. Chelating agents are commercially used in epoxy phenolic adhesives to stabilize the metal interface. These materials generally sacrifice high temperature resistance for improved peel strength. Additives such as guanylate or galates act as chelating agent to inhibit the reaction with iron in metallic substrate, such as stainless steel at high temperatures. The current trend in formulating epoxy phenolic adhesive is to increase the epoxy content for greater toughness and toward using acid accelerator for faster cure. Epoxy phenolic adhesives are generally preferred over other high temperature adhesives such as polyimides and polybenzeimidazoles because of their lower cost and ease of processing. The epoxy phenolic adhesive have moderately good peel strain, which is acceptable for many structural applications. However, the demands for high peel strength and high temperature adhesives such as aerospace honeycomb bonding have resulted in formulations with the addition of thermoplastic modifiers in the epoxy phenolic formulations. The nylons used as modifiers for epoxy adhesives are soluble, semi-crystalline copolymers made from conventional nylon monomers. Conventional crystalline nylon polymers such as nylon 6 or nylon 66 would be incompatible with epoxy resins. The epoxy nylon ratio can vary significantly in the adhesion formulation, but blends containing 30 to 50% by weight of nylon are most common. Higher ratios of nylon will increase tensile shear strain and peel strength measured at temperatures from minus 55 to 80 centigrades. However, temperature and moisture resistance will eventually be degraded by high nylon concentrations. Films are blended containing 30 to 50% by weight of epoxy resins. The nylon used as modifiers for epoxy adhesives are soluble semi-crystalline copolymers made from conventional nylon monomers. Conventional crystalline nylon polymers such as nylon 6 or nylon 66 would be incompatible with epoxy resins. The epoxy-nylon ratio can vary significantly in the adhesive formulation, but blends containing 30 to 50% by weight of nylon are most common. Higher ratios of nylon will increase tensile shear strain and peel strength measured at temperatures from minus 55 to 80 centigrades. However, temperature and moisture resistance will eventually be degraded by high nylon concentrations. Films are blended containing 30 to 50% by weight of epoxy resins. The nylon constituent provides high tensile shear strain as well as high peel strength. Suitable catalysts are dicy and aromatic polyamines. These adhesives have useful properties at low temperatures, but have only moderate good at high temperature properties. The toughness associated with epoxy nylon adhesive is primarily due to hydrogen bonding within the nylon molecules. However, the high polarity that contributes to a high degree of toughness and adhesion also causes water absorption and significant loss of strength from exposure to moist environment. There is also evidence that the toughening action of the nylon is partly due to the reaction of the amide hydrogen with the epoxy ring. These resins can be dissolved in alcohols and other solvents, and they can be melted below their decomposition temperature. A preferred solvent mixture is ethanol plus up to 20% water. Epoxy nylon resins are one of the best materials to use in film and tape adhesives for applications where the surface environment is not severe. Epoxy nylon adhesives offer both high tensile shear and peel strengths. Epoxy nylon adhesives can provide tensile strength greater than 5000 psi and peel strength greater than 15 pounds per inch. In addition, epoxy nylon adhesives have good fatigue and impact resistance. They maintain their tensile lap shear properties at cryogenic temperatures, but the peel strength is poor at low temperatures. Because of their excellent feeling properties and high peel strength, epoxy nylon adhesives are often used to bond aluminum skin to honeycomb cores in aircraft structures. Epoxy nylon adhesive introduced in 1960s were one of the first structural adhesives designed specifically to have high shear strength and extremely high peel strength. These characteristics are achieved by blending epoxy resins with copolymers from the polyimide or nylon resins family, which is noted for toughness and tensile properties. A commercial example of an adhesives grade nylon is DuPont's Zytel 6 1.2. Epoxy nylon adhesives' main advantages are better flexibility and a large increase in peel strength compared with unmodified epoxy adhesives. Epoxy nylon adhesives are limited to a maximum service temperature of 85 centigrade and they exhibit poor creep resistance at that. Possibly their most serious limitation is poor moisture resistance because of the hydrophilic nylon polyamide constituents. The degradation by exposure to moisture occurs with both the cured and uncured adhesives. Not only is low tensile shear strain noticed on moisture aging, but also the mode of failure changes from one of the cohesion to adhesion types. Substrate primers have been used with epoxy nylon adhesives to provide improved moisture resistance. However, they do not achieve the moisture resistance associated with unmodified epoxy or nitrile epoxy adhesives. Epoxy nylon adhesives are generally available as unsupported film or as solvent solutions. Adhesive films are made either by solution casting or by dry mixing and calendering. Common solvent solutions are blends of methanol, water, and furfural alcohol. A curing agent is 2,4-dihydrazino-6-methylamino-S-trazine. Other suitable catalysts are dicy and aromatic polyamines. Typical formulation are shown here for your reference. Polysulfide compounds that are compatible with epoxy resins are liquid elastomers at room temperature. They often contain a high concentration of sulfur linkage that provides these products with their unique chemical properties. Polysulfides can be cured by themselves with an oxidizing agent as a catalyst. A sulfur odor is noticeable during processing, making ventilation important. They can also be used to cure epoxy resins. However, the rate of cure is very slow for a practical adhesive. Thus, polysulfide resins are generally added into epoxy formulation as a modifier to increase flexibility. In applications where maximum flexibility is required, the level of polysulfide may be greater than the epoxy resin present in the formulation. For adhesive systems, the liquid epoxy resins most widely used with LP3 polymers are liquid unmodified and diluent modified bisphenol A resins and liquid blends of bisphenol A and bisphenol F resins. Solid bisphenol A multifunctional and aliphatic diapoxy resins have also been used with these types of resin. Ratios of liquid polysulfide polymer to epoxy are in the range of 1:2 or 2:1. An increase in elongation and impact strain is the result of increased amounts of the liquid polysulfide polymer. The addition of the polysulfide resin acts as both an elastomeric modifier and a diluent for the epoxy resins. The low viscosity of these products can drastically reduce the viscosity of the overall formulation. This provides greater ease of mixing and applications and the ability to be applied and sprayed without a solvent. Suitable curatives for the polysulfide epoxy reactions include liquid aliphatic amines adducts, solid amine adducts, liquid cycloaliphatic amines, liquid amidoamines, liquid aromatic amines, polyamides, and tertiary amines. Primary and secondary amines are preferred for thermal stability and low temperature performance. Not all amines are completely compatible with polysulfide resins. The incomplete amines may require a 3-port adhesive system. The epoxy polysulfide adhesive is usually supplied as a 2-port flowable paste that cures at a rubbery solid at room temperature. These systems can be heavily filled without adversely affecting their properties. Epoxy sulfides are often used in applications requiring a high degree of elongation. These adhesives are generally used to bond concrete in floor, roadways, and airport runways. Other principal uses include sealing applications, bonding of glass, potting, and bonding of rubber to metal. The most significant commercial resins of epoxy polysulfide resin type is LP3 from Toray. The predominant product is a mercaptan-terminated liquid polymer, LP, that contains approximately 37% bound sulfur. The liquid polysulfides are generally added to the liquid epoxy resins component because of possible compatibility problems. Optimum elevated temperature performance is obtained with either an elevated temperature cure or a post-cure. Polysulfide resins combine with epoxy resins to provide adhesives and sealants with excellent flexibility and chemical resistance. These adhesives bond well to many different substrates. Tensile shear strain and elevated temperature properties are low. However, resistance to peel forces and low temperature is very good. Epoxy polysulfide have good adhesive properties down to -100 centigrades, and they stay flexible up to -65 centigrade. The maximum service temperature is about 50 to 85 centigrade, depending on the epoxy concentration in the formulation. And the temperature resistance increases with the epoxy content of the system. Resistance to solvent, oil, and grease, and exterior weathering and aging is superior to that of most thermoplastic elastomers. A typical formulation has been presented for adhesive systems formulated with polysulfide as a modifier for a system where an epoxy-terminated polysulfide has been employed. Epoxy resin may be blended with certain vinyl polymers to improve the impact strain and peel strain of the adhesives. Polyvinyl acetal, such as polyvinyl butyrol and polyvinyl formol, and polyvinyl esters are compatible with diglycidyl ether bisphenol A epoxy resins when added at concentration of 10 to 20% by weight. Vinyl epoxy adhesive have moderate strain at temperatures up to 150 centigrade. Oxidation stability is excellent. Vinyl constituent increase toughness and peel strength. The adhesive is often used for bonding safety glass, aerospace engine structures, and structural panels. The addition of polyvinyl acetal improves the resulting impact resistance and peel strength of the cured adhesives. However, temperature and chemical resistance are sacrificed by the addition of low glass transition temperature vinyl resins. The solubility of the vinyl polymer in the epoxy resins will depend on the molecular weight and the grade of vinyl used. Polyvinyl esters can be dissolved in liquid epoxy resins that are heated to about 100 centigrades or in melted solid epoxy resins. However, most epoxy vinyl blends are normally prepared via solvent solution. The formulated adhesives are generally available as films or solvent solutions. They are commonly used as laminating adhesives for film or metallic foil because of their high peel strengths. A composition consisting of a plasticized polyvinyl chloride copolymer and an epoxy resin can be cured with an aliphatic polyamine, which will cross-link by reacting with both resins. Polyvinyl butyrol is used in combination with thermosetting resins to form tough, strong structural adhesives. The most important adhesives for gluing of metals are bisphenol epoxy resins and phenolic resins modified by the addition of polyvinyl acetals, for example, polyvinyl butyrol and polyvinyl formol. Polyvinyl acetal resins are known for their excellent adhesion to a variety of surfaces. While the principal applications are adhesives for glass and metal, polyvinyl acetal provides structural adhesion for paper, fiber, and plastics. This adhesive property is excellent adhesion to metals. Epoxy-urethane adhesives provide properties when cured that are similar to those of epoxy nylon adhesives, except they offer a major improvement in the moisture resistance. Isocyanate monomers and prepolymers react with the hydroxyl groups on epoxy resins to give tough, flexible hybrids. The reactivities of isocyanate and epoxy resins are similar in that both can be cured with amines or other hydrogen-containing compounds. The epoxy-urethane adhesives have been noted for their excellent adhesion to many high-energy plastic substrates and for their propensity to bond to oily metal substrate. The epoxy-urethane adhesive resists hydrolysis and give useful bond strength up to 100 centigrades. The epoxy-urethane adhesives were developed initially for bonding to oily cold roller steel, but they have given good results on other substrates as well. It is believed that the oil contaminant on the substrate is absorbed into the substrate, into the adhesives, and act as plasticizers. Some epoxy urethane hybrids in 1 and 2 component structural adhesive have had success in the automotive industry where high impact resistance, fatigue resistance, and high bond strength to a variety of substrates are valued characteristics. Blocked isocyanate prepolymers have been mixed with epoxy resins and cured with amines as well. These blocked prepolymers will initially react with the amines to form amine-terminated prepolymers that cross-link with epoxy resins. Urethane amines are also offered commercially for use with epoxy resins to develop hybrid adhesive systems. An acrylate-terminated polyurethane modified epoxy compound and a polyethylene polyamine homologue and fatty acid combination were formulated into a two-component adhesive system. The adhesive is useful for bonding various thermoplastic resins such as ABS, polycarbonate, PPT, PC blends, and PPO. Epoxy polyurethane adhesive have a great deal of toughness. They have high elongation and very good peel strength and impact properties. They also have a relatively high degree of tensile strength given their elongation. These adhesives bond well to flexible substrates such as plastics. They also bond well to oily surfaces. The main market for epoxy polyurethane adhesive is automotive industry. There have been many attempts to couple the integrity, heat, and chemical resistance of epoxies with the toughness and peel strength of the polyurethanes. However, these attempts have often resulted in adhesive systems that display the worst properties of the parent resins rather than the best properties. This is due primarily to the significantly different reaction rates between NCO groups of the isocyanate and the epoxy groups of the epoxy molecule with the common curing agents. The isocyanate reaction is several orders of magnitude faster than the epoxy reaction. Hence, attempt to cure mixture of epoxy and isocyanate resins must provide for essentially coupled consumption of all cyanide groups before any of the epoxy rings can react. Another toughened epoxy formulation comes from mixtures of epoxies and urethane oligomers with pendant epoxy groups. Curing of the pendant epoxy groups units, the urethane and non-urethane components through conventional epoxy reactions to give tough, durable films. This approach, however, resulted in a decrease in high temperature strain and chemical resistance, although 500 to 1000 psi shear strain is achieved at temperatures in the range of 80 to 100 centigrade. Straight polyurethane adhesives show much poorer strain at the temperatures in this range. The number of possible hybrid systems that can be manufactured with epoxy resins is nearly infinite, and many adhesive formulations have been attempted in a quest to improve the main advantages of a cured epoxy: brittleness and rigidity. Functionalized liquid polybutadiene derivatives have been developed as hybrid flexibilizers for epoxy resins. Carboxyl-terminated butadiene acrylonitrile polymers, butadiene homopolymers, and maleic anhydride amino acid grafted butadiene homopolymers have been used as flexibilizers to impart good low temperature strain and water resistance to diglycidyl ether bisphenol A based epoxy adhesives. An epoxy system toughened by polybutadiene with maleic anhydride is claimed to provide a hydrophobic backbone, low viscosity, softness, and high tensile strain and adhesion. Epoxy-PVC plastisols are a type of PVC plastisol adhesive that is used in large quantities in the automotive industry. It is used to bond sheet steel into inner stiffener panels and to seal around the crimped panel edges. These adhesives are called Hershey drops in the trade because of the characteristic and geometry of the droplets. The epoxy PVC plastisols type is a mixture of a plastisols grade PVC powder, primary PVC plasticizers, for example, dioctyl phthalates, a liquid diglycidyl ether bisphenol A resins, thickeners, stabilizers, surfactants, and other additives. The epoxy PVC Plastisols adhesives are soft and flexible after cure. Their important properties is their low cost and long-term toughness and adhesion, as well as adhesion to oily steel. Fluoroepoxies have gained interest because of the unique adhesion properties that can be provided by the fluorine group. In general, these have focused on adhesive systems that have a lower surface tension than unmodified epoxy or have significant hydrophobicity to resist exposure in moist environment. The use of fluoroepoxies is most advantageous in bonding fluorocarbons such as polytetrafluoroethylene to the epoxy. Good bond strengths are achieved on fluorocarbons without the need to surface treat the substrate because the surface tension of the fluoroepoxy adhesion is reduced from about 45 of normal epoxy to 33 dyne per centimeter for fluoroepoxy. Fluoroepoxy resins have also been developed that when cured with silicone amines or fluoroanitrides show substantial hydrophobicity. As the resin's fluorocarbon content is increased, so its hydrophobicity is also increased. Adhesives made with these compounds showed much less degradation in glass transition temperature as a fraction of exposure to high moisture environments. Epoxy-silicone hybrid resins have generally been developed for use in the molding of microelectronics packages. These resins have moderated strength but exhibit a degree of elongation of about 60% at break. Certain adhesive formulation have been developed by the reaction of silicone polymers containing amine termination with epoxy resins. The resulting products exhibit good flexibility with steel, maintaining good chemical and thermal stability. Epoxy-acrylic hybrid systems have been developed with major applications in the automotive industry. The system may be one component or two component adhesives, or it may be a one component adhesive taking the form of a film or a paste. In one instance, the hybrid takes the form of a film in which the acrylic, the monometacrylic of diglycidyl bisphenol A has been polymerized by UV light. The epoxy is a diglycidyl bisphenol A dicy-laden curing system containing a polyvinyl phenol amine complex. After irradiation, the film has good tack and will adhere to oily steel. It can be cured at 180 centigrade for 30 minutes to achieve final strength. And other resins that are used to modify epoxy formulates are polyesters, terminal carboxyl groups, aniline formaldehyde, terminal amine groups, urea formaldehyde, methylol groups, and furfural resins, methylol groups. These hybrids generally yield improved flexibility and toughness, but they are more commonly used in epoxy coating formulation than in adhesive systems. Thanks for your attention. I hope you enjoy this video. Please share your thoughts, questions, or comments, and I will come back to you soon.